Welcome to another episode of Fort Bend Mathematics Tutoring. Take a moment to soothe your nerves. Remember, these is just numbers. They can't hurt nobody.
Hello ladies and gentlemen, this is Mr. Witt with Fort Bend Tutoring, and today's tutorial is going to be about finding the domain of a function. Alright, well, anytime you're asked about the domain, ladies and gentlemen, they're asking you, what can x be? That's right. What can x be? What are the values of x of this function? That's what they want to know, ladies and gentlemen. So before you can find out what the domain is, it's kind of faster to go ahead and find out what the domain cannot be. That's right. Let's find out what it can't be first, and then that'll help us find out what the domain actually is. The reason for this is that the domain in many cases is an infinite amount of numbers. However, in many cases, usually finding out what the domain cannot be is usually one number or maybe even two numbers that you need to exclude. That's why you need to be aware of what we call domain restrictions. And some of the common domain restrictions are: 1, the denominator of a fraction cannot equal to 0. You can't have 0 in the denominator of a fraction. It's undefined. It doesn't make any sense. You can't have part of something that never existed. Okay, so the denominator in any fraction can never equal to 0. That's undefined. When it comes to even roots, and we're not dealing with imaginary numbers here, so anytime you're asked for the domain restrictions, you're dealing with real values, okay, not imaginary numbers. So you can't have negative values in even roots. In other words, I can't take the square root of a negative number. All right, so we want to avoid situations like that. Anytime you're dealing with natural logs or logarithms, whether they're common logs or not, you cannot take the log of 0 or a negative number. All right, so if you're going to take the log of anything, it needs to be a positive value. All right, or it just won't work. In other words, it's undefined. All right, so let's go ahead and take a look at some of our problems that I have for you today, okay? All right. Starting out, we have the function number 1, and it's always good to be aware of your basic functions, and you should recognize that this is a linear equation. That's right, the function that you're looking at right here, that y equals negative 2/3 x minus 5, that's a line. It's a linear equation. More importantly, you want to be able to determine whether or not this domain can be restricted by one of the 3 restrictions that I showed you on the previous page. In other words, is our variable in the denominator? No, it's not. Okay. Am I trying to take the natural log of this value? No. Am I trying to take the square root of this value? No. So that means that there's nothing that can stop me from plugging in any number into this equation right here. Nothing. Nothing's going to make this equation undefined. Therefore, the domain for this function is going to be negative infinity to positive infinity. In other words, all real numbers. That's right. Any number, ladies and gentlemen, and you can go ahead and use the all real number symbol here. Any number can be plugged into this equation, and that's it. That's all you need to be aware of. That's right. I'm going to go ahead and box this up in red. You got it. So you can give your instructor negative infinity to positive infinity. You can give them the all real symbol there if they're accepting that, or you can simply write out all real numbers. Any of those would be acceptable. You can plug in anything into this equation, ladies and gentlemen, anything into this function, and it'll be a-okay. That's number 1. Let's check out the next problem. In problem number 2, we have a rational function. This is y equals to 3 over x. And the first thing you're looking for is to see if there is a domain restriction. Yeah, and we definitely have one. You can't have 0 in the denominator of a fraction. You just can't have it, okay? So anytime you're given a rational function like this, you're going to set the denominator not equal to 0. Why? The denominator of a fraction cannot equal to 0. So this is going to be my setup. I'm going to say that x cannot equal to 0. Yeah. It can't equal to 0. So whatever the denominator is that contains your variable, go ahead and set it not equal to 0 and then solve for x. Well, in this case, my x is already solved for. Okay, and to help you out with your interval notation here, it may be a good idea to go ahead and set this up on a number line. So what I'm going to do is I'm going to show that at 0, my value of x can never equal to that, because that'll make my original function undefined. But everything to the left of 0 is good, and everything to the right of 0 is good. So in writing my answer in interval notation, I'll say that this left region here will be defined as negative infinity to 0, not including 0, union the right part of this region, which is going to be 0 to positive infinity. And this is the domain, ladies and gentlemen, in interval notation. That's it. All right. So most teachers will want you to write it in interval notation. Some teachers will go ahead and let you write the domain by saying that x is such that x cannot equal to 0. All right. So some will accept this. Most will want you to write it in interval notation. Yeah, just like that. Okay. All right, ladies and gentlemen, let's continue moving along. I got other examples for you. Starting with problem number 3. We have f of x equals to 3x squared minus 5x plus 6. All right. Now, this is a quadratic function, and you should know that. But more importantly is that, are there any domain restrictions in this? And the answer to that question is no. I don't have a variable in the denominator of a fraction. I'm not trying to take the square root of a value here. I don't have that situation. There are no natural logs in this problem. I don't have any of those concerns at all. Therefore, the domain, yeah, you got it. It's negative infinity to positive infinity. If you don't find any domain restrictions or possibilities for domain restrictions, then your domain is going to be all real numbers. That's it. Yeah, I'm going to put a box around this. Oh, you wanted to write that all real numbers symbol, that Rough Rider symbol? There you go. There you go. You can take either one of those and take it to the bank. All right, just like that. That was problem number 3. Yeah, let's continue with this. I am having too much fun with you today. Here in problem number 4, we have y equals to negative square root of x. Y equals to negative square root of x. So I'm trying to take the square root of my variable. Okay. Anytime I'm trying to take the even root of a value, if I'm dealing with real numbers, that value can't be negative. So therefore, anytime you have a square root, an even root, that can mean that it could be a 4th root, a 6th root. If it's an even root, ladies and gentlemen, you're going to set this value underneath the radical greater than or equal to 0 and solve for it. It'll look like this. X is greater than or equal to 0. And then you're going to solve for x. My x is solved for. That means that in some classes, this is the answer for the domain, that x has to be greater than or equal to 0. However, ladies and gentlemen, let's say that you're in a class where that's not going to fly. You got to show your interval notation. So at 0 on my number line, I want to include that value. I'm going to have a bracket here, or you can use a closed circle. And since the solutions must be greater than or equal to 0, we can go ahead and shade to the right to show this will be the area where the solutions lie. In other words, the area where my domain is. And then to write this in interval notation, we'll do the following. I'll have my bracket. I'll have 0 to positive infinity. And that's it. All right. There you go, ladies and gentlemen. I'm putting a red box around this. That's right. That's the domain, ladies and gentlemen. Once again, anytime you have a radical, set your radicand, the value underneath the radical symbol, the square root sign, set that greater than or equal to 0. That's what you need to do. Let's continue. Let us continue on with problem number 5. In problem number 5, I have y equals to the cube root of 5x minus 8. Now remember, I just said that you can never take the square root of a negative value when you're dealing with these functions, okay? So I never said anything about the odd roots, right? Remember, that's because the odd roots are a-okay. It's okay to take the cube root of a negative number. It's all right. There are no restrictions on this problem. There are no restrictions on this problem. So, therefore, your domain is negative infinity to positive infinity. There's nothing stopping you from plugging in any value into this function. Nothing. The domain, negative infinity to positive infinity. Oh, these infinity signs are jacked up. Yes, I know that, but it's the best I can do. All right, so Rough Rider symbol out of the way, ladies and gentlemen. That's it. There's nothing preventing you from plugging in any value. All real numbers, anything can be plugged into that problem. Let's continue. In problem number 6, we have f of x equals to the square root of x plus 2 plus 16. And anytime I have a square root sign, a radical, an even root, I want to be aware first, is this an even root? Yeah, it is. And then second, I want to make sure that the value underneath the symbol here is going to be at least 0. Okay? It has to be greater than or equal to 0. So therefore, x plus 2, guess what? You have to be greater than or equal to 0. That's right. You must be greater than or equal to 0. So now I'm going to solve for x. So I'll be subtracting 2 to both sides here, additive inverse. This gives me x is greater than or equal to -2. And ladies and gentlemen, this is the domain. My values of x, the domain, must be greater than or equal to -2. That's it. Yeah. Oh, you want to see it on the number line? Okay. All right. Stop being bossy. You guys are so bossy, man. Always bossing me around. You're not the boss of me. You are not the boss of me. So anyway, on a number line, it can be -2 and anything greater than -2. So I'm going to go ahead and show a bracket here, or you can use a closed circle, and everything will have to lie to the right of that, okay, going to positive infinity. So using interval notation, thank you, that's going to be a bracket, -2 to positive infinity. Infinities, you always use parentheses to open or close when you're dealing with infinities. Okay, so if it was negative infinity, you better have a parenthesis next to it. If it's positive infinity, parentheses. All right, so that's going to be the answer. That's the domain. I got a box around this. Remember, today's lesson is only focusing on finding the domain. That's it, all right? So if you want some other stuff, you got to watch another one of the videos we have. Okay, so continuing on, let's check this out. In problem number 7, we have a rational function, but within this rational function, you are dealing with an absolute value in the denominator. Okay, your concern is I can't have 0 in the denominator of a fraction. That's the domain restriction that we need to be concerned with. There is no domain restriction on our absolute value. You can plug in any number in there. You don't care. You don't care. But what you do care about is that since this value is in the denominator, it can't equal to 0. It just can't. So what you'll do is you'll just set this denominator not equal to 0. That denominator, yeah, you can't equal to 0. You just can't do it. In fact, I'm going to go ahead and solve for this. So dealing with this absolute value right here, we already know that since it's already set to 0, we can just drop the absolute value signs. That's right. There is no negative version of this value right here. Okay. So it's only going to be set equal to 0. It can only equal to 0. All right. So therefore, we're going to just say x plus 4 can't equal to 0, and then we'll solve for it. That's it. Okay. So x, we find, cannot equal to -4. That's right. X can't equal to -4 is the domain. And because of that, since we're excluding -4, that means that everything to the left of -4 is good and everything to the right of -4 is good, which means in interval notation, the answer will look like this. It'll be -infinity to -4 union -4 to positive infinity. Yep, just like that. Okay, I'm gonna put a red box around this. There we go. There we go. So yes, you have the generic way to write the domain, or a simpler way, and then the way you're supposed to write it. Yeah, the interval notation way. That's the way that most teachers dealing with this will want. Okay, so there you have it. That's right. Okay, so let's move on. Problem number 8. Doesn't this function look juicy? Well, it does. Y equals to 7x squared minus 6x plus 3 divided by x squared plus 4. You are concerned about the denominator. That's right. You're trying to find what x can be, which means that you're looking for a domain restriction. And since overall this is just a fraction, you know you can't have 0 in the denominator. You can't have 0 in the denominator of this fraction, okay? Or any fraction for that matter. So set the denominator not equal to 0. So I'll have x squared plus 4. Yeah, you can't equal to 0. It's not happening, brother. So solve for x. That's what we'll do next. So I'll start by subtracting 4 to both sides of the equation here. I'll have x squared equals to -4, and lo and behold, ladies and gentlemen, check this out. If I try to take the square root of this, yeah, implementing the square root property, yeah, you would end up with an imaginary number. See, I'm trying to take the square root of a negative number, which means that it's not possible to get a real number to give you a value of 0 in the denominator. See, with this x squared plus 4, let's say I have a negative number, right? What will happen to the negative number when I square it? Well, it'll become positive, right? So a positive plus a positive will still give me a positive number. Okay, all right, let's look at this then. Let's say I plug in a positive number. It'll still stay positive, right? Okay, let's say if I plug in 0. 0 squared is still 0, right? I'll still end up with a positive 4. In other words, ladies and gentlemen, there's no way that I can get 0 in this denominator. There's no way I can get 0 in the denominator of this function. Therefore, I can plug in any number into the function. That's right, the domain of this function is all real numbers. That's it. Domain, yeah, you're all real numbers. I can plug anything into this. There's no way I can generate a 0 in the denominator. And because of that, the domain is all real numbers. Yeah, just like that. That's problem number 8, ladies and gentlemen. I hope this is helping. I want to help. Okay? Let's continue. Here we have problem number 9. In problem number 9, we have y equals to x squared plus 5x plus 4 divided by x squared minus 4. Once again, I have a fraction. Once again, I can't let the denominator equal to 0. It's undefined in that situation. So therefore, you set the denominator not equal to 0. So I'll have x squared minus 4 not equal to 0. And lo and behold, ladies and gentlemen, this is factorable. Okay, now, yeah, you could use the square root property, but I'm going to factor. So this is going to be x plus 2 times x minus 2. And it still can't equal to 0. Using the zero factor property, okay, I'm going to set each one of these factors not equal to 0. So this will be x plus 2 cannot equal to 0, and x minus 2 cannot equal to 0. After solving for both of these, you'll find out that x cannot equal to negative 2, and x cannot equal to positive 2. All right. That being the case, let's look at what the number line would look like in this situation. You would have your number line here, you would have negative 2 and positive 2, and you know that you need to avoid negative 2 and positive 2. But every number other than those two values is good to go in this equation. So that means that everything to the left of negative 2 is good, everything in between negative 2 and 2 is good, and everything to the right of 2 is good. So this is what you need to represent in your interval notation. So yeah, you could have written your answer like this to say that, hey, I need to exclude negative 2 and positive 2. Yeah, but if you want to be a boss, you want to write it in interval notation. So your answer will look just like this. For this left region, you'll write your interval notation as negative infinity to negative 2. Then you'll union that for the middle portion here, the values between negative 2 and positive 2. So I'll have negative 2 to 2. Then I want to take care of the right portion, so I'll have union 2 to positive infinity. And this is the domain, ladies and gentlemen, in interval notation. That's right. Now notice how I use my number line to ensure that I'm keeping up with all the regions that I need to represent in interval notation. All right, it helps me out, so you may want to try it. That's problem number 9, ladies and gentlemen. Problem number 9. All right, problem number 10. We have f of x equals to the natural log of x plus 3. When you're dealing with logarithms and natural logs, ladies and gentlemen, you can't take the natural log or log of 0 or a negative number. You just can't do it. Therefore, the setup for any of these problems where you have an independent variable, you'll be placing what's inside the parentheses greater than 0. So I have x plus 3 has to be greater than 0. It has to be greater than 0 because whatever this value is, it has to be greater than 0 in order for this function to be defined, all right, in order for it to be a valid equation. All right, so let's go ahead and solve for x by subtracting 3 to both sides here. And I find that x has to be greater than negative 3, okay? That's the domain. That's it. X has to be greater than negative 3. So in interval notation, it'll be from negative 3 to positive infinity. And that's it. That's it. That's the domain. That's how you do it, ladies and gentlemen. Just like that. All right. Next up, problem number 11. We have f of x equals to the square root of x plus 3 divided by x squared plus 5x plus 6. Here in this problem, you have multiple domain restrictions. Not only do I need to be concerned about the square root sign because I can't take the square root of a negative number, I also cannot have 0 in the denominator of this fraction. So I need to be concerned about all of those issues. So let's start with the radical here. I know with my square root that x plus 3 will have to be greater than or equal to 0. I also know that with the denominator, x squared plus 5x plus 6, yeah, that can't equal to 0. So I need to solve for x in this inequality and in this equation here. So that being the case, I'm going to go ahead and subtract 3 to both sides. All right. And I end up with x needing to be greater than or equal to -3. All right. In addition to that, if you factor your trinomial here, you'll have x plus 3 times x plus 2, and all of that can't equal to 0. So after solving for that, you'll know that x cannot equal to -3 and x cannot equal to -2. And all of this needs to be kept in mind, ladies and gentlemen. All right, so let's see what that looks like on a number line. All right, so on my number line here, I'll have -3, and I'll also have -2. All right. Now, according to the inequality, I know that x has to be greater than or equal to -3. But right here, dealing with this equation, it simply says x cannot equal to -3. So that means we'll have an open circle here at -3, but according to our inequality, things can be greater than -3 as well, though. So, right? So we know that we can have it equal to -3, but as we approach this -2, we find that, lo and behold, x cannot equal to -2 also. So that'll be an open circle here at -2. We have to avoid the -2 as well, because that will create a 0 in the denominator. So therefore, we're skipping -2, but remember, because of this inequality here, things would continue from there to positive infinity. So we're still avoiding the -3 and the -2, but including the fact that things can be greater than or equal to -3. All right? So this, ladies and gentlemen, is my domain. That's right. So for interval notation, you'll do the following. You'll have -3 to -2 union -2 to positive infinity. And this is the domain. All right. So because of our original function, we had to be concerned about the square root sign in the numerator, as well as having 0 in the denominator. And with this quadratic expression, that meant that we would need to factor it out or solve for x using either completing the square or the quadratic equation if it wasn't factorable. But fortunately for us, it was factorable, so we used the 0 factor property. All of these things that I'm mentioning for solving the quadratic equation, you can find a video from us for it. All right, so check those things out. I'll put them in the description box. All right, so there you go. Let's look at the next problem. In problem number 12, we have f of x equals to 2x squared minus 3x plus 7 divided by x cubed minus 8. Yeah, in the denominator we have a difference of cubes. A difference of cubes. So what you'll want to do here is you'll want to be able to factor this out. All right, so in the denominator, I want to say that x cubed minus 8, yeah, you can't equal to 0. It's not happening. So therefore, I'm going to go ahead and attempt to solve this by factoring it. So I know that being as though this is a difference of cubes, factoring this would give me x minus 2 times x squared plus 2x plus 4, and that cannot equal to 0. All right. That being the case, ladies and gentlemen, you have two factors here, and you can separate them and solve for them. Here, I'll have x minus 2 cannot equal to 0, and I also will have x squared plus 2x plus 4. Yeah, you can't equal to 0 either. So the first equation, yeah, that's simple. You just simply add 2 to both sides, right? And you'll find out that x cannot equal to positive 2. Over here on the right side, yeah, I'm thinking that this is not factorable, and in addition to that, I'm thinking it's not possible with real numbers. So let's go ahead and look at the discriminant, all right? And that'll tell me whether or not I'll have real numbers that I could solve for. So if the a value is 1, the b value is 2, and the c value is 4, I know that my discriminant is going to be b squared minus 4ac. This will tell me whether or not I'll have a real solution. That way I can just ignore it if it isn't. So plugging these values in, I'll have 2 squared minus 4 times 1 times 4. Yeah, and lo and behold, you'll have 4 minus 16. So this gives you negative 12. This means this is not happening over here, ladies and gentlemen. Yeah, it's not a real number. That's not a real solution that I need to be concerned with. Remember, when you're dealing with the domain, you're dealing with real numbers. So anytime you solve for x and you end up with an imaginary number, that's not going to be included in the domain. In other words, you can ignore it. All right, just don't even worry about it. So our only real number that we need to be concerned with in this domain is the number 2, which means x cannot equal to 2. But any other number than 2, it can. So that means that my interval notation for this problem is going to be negative infinity to 2 union 2 to positive infinity. In other words, I'm excluding 2, but every other value is good. So depending on how your teacher wants you to write the domain, you can just simply say that x cannot equal to 2, but most likely you'll be using interval notation where we have negative infinity to 2, union 2 to positive infinity. And that's problem number 12. All right, so now let's take a look at problem number 13. In problem number 13, we have y equals to x minus 2 divided by the natural log of x. Now we're looking for the domain, which means that we need to focus on the restrictions. In this problem, we have more than one domain restriction going on. For one, I know that I can't have 0 in the denominator of this fraction. Can't happen. I just can't have it. In addition to that, I can't take the natural log of 0 or a negative value. So I also need to be mindful of that as well. So we're going to set up 2 conditions here. 1, the natural log of x cannot equal to 0. And then our value of x has to be greater than 0 because once again, when I'm taking the natural log of this value, it cannot equal to 0 and it can't be negative. It has to be a positive value. With these 2 conditions, my inequality is already solved for. I already know that x has to be greater than 0 already because of the natural log. In addition to that, I need to find out what will make this value of the natural log of x 0 so I can avoid it. Therefore, if I'm solving for the left equation here, I'm going to exponentialize this and I'm going to have e to the natural log of x cannot equal to e to the 0 power. What will happen with this is that the e and the natural log cancels out and I have x cannot equal to 1. All right, so here I found that x cannot equal to 1 in addition to the fact that x has to be greater than 0. If we were to look at this on a number line, we'll end up with the following. On my number line here, I have 2 values. I have 0 and I have 1. I know that x has to be greater than 0 and also that x cannot equal to 1. So therefore, I'm going to have an open circle here at 1, and then from there, I'll have parentheses at 0, not including 0, and I'll be shading toward the right. I'm going to skip over this 1 here because it can't equal to 1, and then everything after that. So this is going to be the solutions for my domain here. If I were to write this in interval notation, it would be from 0 to 1, not including 1, union 1 to positive infinity. And this is going to be the domain for problem number 13. Once again, we had to avoid getting 0 in the denominator of the fraction, and that's what the value of 1 is doing. If I have the natural log of 1, that equals to 0. So I can't have 1 as a result here. That's why x cannot equal to 1. In addition to that, you can't take the natural log of 0 or a negative number. These values must be positive. So that's why we had to go ahead and say that x has to be greater than 0. And then the intersection of that looks like the following on your number line here, that you're going to have everything greater than 0, you're going to avoid 1, but then everything after 1 is going to be a valid value of our domain here. All right, so we end up with our interval notation from 0 to 1, union 1 to positive infinity, and that's problem number 13. All right, let's move on to problem number 14. In problem number 14, I have y equals to log base 6 of x squared minus 3x plus 2. Recall that anytime you're dealing with a natural log or a logarithm, a common logarithm, the value that you're trying to take the log of cannot be 0 or negative. Therefore, we want to set this trinomial within the parentheses here greater than 0. So I'll have it set up like so. It'll be x squared minus 3x plus 2 has to be greater than 0. So what you're ending up with now is a quadratic inequality. And with quadratic inequalities, we'll need to find out what our critical values are. So therefore, I'm going to factor this first. I'm looking for 2 factors of 2 that will add to give me 3. So that'll be 2 and 1. So I'll set it up as x minus 2 times x minus 1 has to be greater than 0. From there, setting each one of these factors equal to 0, that'll give us our critical values. We'll have x minus 2 equals to 0 and x minus 1 equals to 0, and then we'll solve for each one of these. All right, so I found out my critical value is 2, and I already know that my critical value is going to also be positive 1. So 1 and 2 is what we need to be concerned with on our sign chart that I'm about to set up here. So I have my number line, and on my number line I have the numbers 1 and 2, okay? From here, I'm going to show that my two factors, one, x minus 2, and the other one, x minus 1, with the first factor of x minus 2, I'll end up with a value of 0 when x equals to 2. When x equals to 1, the second factor will be 0, and then I'm going to use a test value, and that'll let me know what signs I'll end up with for each of my factors. So I'm going to use a value of 0 as a test value. Next, I'll be plugging in this test value into the factors to find out the sign of the result. So here I have 0 minus 2. That'll give me a negative value. So I'll end up with negative values until I get to this 0, and then they become positive. Plugging in 0 into the second factor, 0 minus 1 is going to be a negative value until I get to this 0 here. Then after that, they'll become positive. And recall that these two factors are multiplying to get a positive result. That's what you want. So therefore, a negative times a negative is a positive result. A negative times a positive is a negative result. And then a positive times a positive is a positive result. So notice that when my values of x are less than 1, I'll end up with a positive answer. And when my values are greater than 2, I'll also end up with a positive answer, which is what I want for my result here. So my result will be, in interval notation, negative infinity to 1 union 2 to positive infinity. And this is the answer here in interval notation. Let's go ahead and put a red box around this. There we go. All right, just like that. So because we were dealing with this quadratic inequality to find out what values were going to give us a positive result inside of the parentheses here, we had to use our sign chart to be able to identify the regions where these two factors will multiply together to give us positive results. And that occurs when x is less than 1, and it also occurs when x is greater than 2. And in interval notation, you'll end up with negative infinity to 1 union 2 to positive infinity. And that does it for problem number 14. On to the next one. In problem number 15, we have the following function. We have f of x equals to the absolute value of x plus 5 minus 3. Yeah, so check out my graph, right? You see that? It's a V shape, absolute value. What you want is the domain, right? So what we're looking for are values of x. What are the values of x in this function here, in this graph even? Now notice that we have arrows going up to the left and going up to the right in that V shape. This means, ladies and gentlemen, that this continues in this direction infinitely, as well as it continuing in that direction infinitely as well. That means that eventually, ladies and gentlemen, it's going to hit all the x values. There's not going to be an x value that will escape this function's wrath. There is no value that will not be able to go into this function. In other words, if you looked at the original function here, there is nothing that will restrict the domain. All right, and even your graph shows this. So if you're looking at a graph, even if you didn't have this function, because this graph goes on forever to the left and the right and doesn't exclude anything in the middle, your domain is all real numbers. All right, so here, there you go. Rough Rider symbol or interval notation. There you go, there you go. All right, that's the domain. That's it. That's what they wanted to know. I'm putting a red box around here. I like putting boxes around my answers. I just do. All right, let's go on to problem number 16. In problem number 16, we have the following graph and its function. It's right there. Y equals to the square root of x minus 2. But even if I didn't see this function, I see the graph that has an endpoint at 2, 0 is going to go on forever to the right. That's it. That means that it begins at 2 and ends at positive infinity. That is my domain. That's it. I will include the 2 with a bracket that includes that value of 2, and it goes to positive infinity. And that's it. And yes, you could have found that out just using the function and setting it greater than or equal to 0. You still would have found that your domain is from 2 to positive infinity, including 2. All right, let's box up this domain. All right, no escape for you. Continuing on, problem number 17, we have the following. We have the natural log of x minus x squared. Remember that the domain restriction for a natural log or any logarithm is that the value has to be greater than 0. greater than 0. So that's exactly what we'll do with this value here. We'll show that x minus x squared has to be greater than 0. That's right. And knowing that this can be factored on the left side here, I'll factor out an x to find that this is x times 1 minus x. That must be greater than 0. Now, because we have an inequality here, and a quadratic inequality at that, I'll be needing to use my sign chart again. All right. I know that my critical values are going to be 0 for that first factor, and it's going to be positive 1 for that second factor. So those are the critical values I need to be aware of. And if you need to brush up on quadratic inequalities, yeah, click this link down right here. All right, and watch that video so that you can follow the steps that I'm doing here. Okay. So number line is coming up next. My number line. I have my two values. One is 0, the other one is 1. Okay, and I have two factors. I have x and I also have 1 minus x. And what I'll be doing next is coming up with a test value that I'll say is -1. That's going to be my test value. I'll plug that into my factors. I do know that at 0, my first factor is going to be 0. I know that at positive 1, my second factor will be 0, and plugging in -1 into the first factor will give me a negative result. So I'll be negative until I get to 0, and then you'll become positive from there. Plugging in a -1 into the second factor, yeah, that gives me a positive 2. See, 1 minus -1 is positive 2. So therefore I have a positive value here, and it'll be positive until I get to that positive 1, and then after that, yeah, you'll have negative results from there. That's right. So remember, these two factors are multiplying together, and the result of that product, you need that to be greater than 0. Okay? So a negative times a positive is a negative result. A positive times a positive is a positive result. And a positive times a negative gives you a negative result. Just like that. And we want our values to be greater than 0, which means I only want the positive results. That means that this solution lies between 0 and 1. That's it. Okay, there's your answer. There's your domain. Those are the values that you need. So in interval notation, we'll have from 0 to 1 and done. That's it, ladies and gentlemen. That's the domain of this function right here. That's it. That's how you write it. Done and done. Okay. In problem number 18. We have h of x equals to the square root of x minus 2 minus the natural log of 10 minus x. In this function, ladies and gentlemen, you have two domain restrictions. Not only do you need to be concerned about the square root sign, okay, but you also need to be concerned about the natural log here. That means that x minus 2 has to be greater than or equal to 0, and that means that 10 minus x has to be greater than 0. So it's okay to have a value of 0 underneath your square root sign. It's not okay to have a value of 0 when you're dealing with a natural log or a logarithm. So solving for each one of these inequalities, I'll be adding 2 to both sides here. I'll end up with x is greater than or equal to 2. And in this second inequality, I'll be subtracting 10 to both sides to get x is greater than -10. And then dividing both sides by -1, you'll find that x is less than positive 10. All right. So these are my two conditions that we'll place on a number line. All right. So let's check that out. So I have my two values, 2 and 10. Starting from 2, we have x is greater than or equal to 2. So I'm going to use a bracket. Okay. And it's going to be shading to the right. All right. And just in case you were curious, this is an and situation right here. Not only does x have to be greater than or equal to 2, it also has to be less than 10. So this is an and situation, and you want the intersection of both. You want the common solutions from both of these inequalities. That's what we're looking for. As we approach 10, we know that x has to be less than 10, right? So that means I'll be using parentheses here. And so at this juncture, we're done. That's the domain, ladies and gentlemen. So my answer is including 2 with a bracket, and we're going to positive 10 and approaching 10, but not ever equal to 10. So that's why we use parentheses. That's the answer. That's it, ladies and gentlemen. And that does it for today's tutorial on finding the domain of a function. I tried to be as thorough as possible and give you a lot of examples. And as always, please rate, comment, and subscribe. And as always, if you're able, please donate. That helps us bring you more free math tutorials from Fort Bend Tutoring. Peace.
We certainly hope you enjoyed today's mathematics presentations. Did you learn anything? Do you need to review your notes? Take a deep breath and congratulate yourself. I am learning mathematics.